Greetings everyone. Today we're going to be talking more about conservation of momentum and energy. And in this case we're going to be talking about coefficient of restitution and explosive separations. So in the first video, let's consider dropping a ping pong ball. So in this video, we took a few measurements. We started with an initial height of 60 centimeters. And then we dropped it, and after some time it reached another maximum height. So it didn't bounce all the way back up to the 60 centimeters. It only bounced up to this 47 centimeters. So we're going to consider what's going on here. Why didn't it bounce up all the way? And then consider what happens on the second bounce as well. And from this we'll calculate the speed of the ball and the coefficient of the restitution of this ping pong ball. So let's go ahead and write out some of the information that we're given here. So at t equals 0, we know that the ball is at x equals 0.6 meters. So let's go ahead and make a rough sketch here of what's going on. So here's our initial t equals 0. The ball falls down, has a collision with the table, and then bounces back up. And at some later time, t1, right, it reaches another height, but not quite as high as it started off with. So let's label our x-axes. So we're just using x pointing up is going to be positive. So in this case, gravity is down. Okay, so then the next time that it reaches a maximum is 0.7 seconds. And the next maximum height that it gets to is this 0.47 meters. So if we just think about what's happening here, we know that energy isn't being conserved. If this were a perfectly elastic collision between the ping pong ball and the table, we would expect that the ball would bounce back exactly as high as it could, as high as it initially was. So some energy is being lost. And what represents this is this coefficient of restitution, which is this little e, and it's given by v relative final over v relative initial. And this works not only in the case where we have a ball bouncing against another object, but it can also be like two cars colliding elastically. But this is the general definition that we have. So if we want to find out the coefficient of restitution, we need to know how fast is it going before the collision, how fast is it going after the collision. But in this case, all we have are times that it gets to the top of the peaks and these peak heights, basically. But this is enough information for us. If we go back to our kinematic equations, we get this v final squared is v initial squared plus 2a, the change in distance. So in this case, our acceleration is gravity. And let's just consider the drop. So here we're starting off with v equals 0. So that's going to tell us this guy is 0. This guy is gravity. And this v final, that's what we're looking for. And we know delta x. So this is exactly what we want. So we're going to end up with this v final is going to be the square root of this 2a delta x, which is square root of 2 times 9.81 times this delta x. So in this case, both g and delta x are negative because you start here and then now you go down here. So delta x is negative and g is negative because it's pointing down. So you see our delta x is pointing down too. So those two cancel each other. So here's our 0.6 meters. And so we end up with a velocity of 3.4 0.03 meters per second. All right, and now we can do the same thing for the bounce back up. In this case, delta x is positive because we're moving up. And what we're looking for is actually going to be v initial. But we start with the same equation. So this is the bounce back up. So it reaches at the top, at the apex of its trajectory, this guy is 0. So we're going to get this v initial squared is going to be minus 2a delta x. So in this case, a is still negative, but this minus sign kind of cancels it out. So we pretty much end up with the same equation, 2 times 9.81. But in this case, our delta x is not 0.6. It is this 0.47. So we're going to end up with 3.03 meters per second. All right, so we see that indeed the kinetic energy of the ball was not conserved before and after the collision because these v's are not constant with each other. So what we could do is calculate this E. E is going to be v rel final, so that's 3.03 meters per second. And this is the relative velocity because we have this, the ball is moving down, and then the table isn't moving up towards it, so the relative speed between the ball and the table is just this 3.03. And now we have 3.43 meters per second. When we calculate this, we get 0.88. And what are the units of this? There are no units, so coefficient of restitution is a unitless quantity. So our ping pong ball has a coefficient of restitution of 0.88. In this case, we're going to be dropping a golf ball. You can go ahead and take your guess. Is this going to bounce up from the table higher or lower than the ping pong ball did? So we can see that the first bounce, it only got up to 0.33 meters, whereas the ping pong ball got up 0.47 meters. So let's calculate the golf ball's coefficient of restitution. So again, the coefficient of restitution is v rel final over v relative initial. And what we found before was that we both calculated these velocities, right? The velocity coming down, right, was a square root of 2gh from the drop height, and v going up was square root of 2g, the height of the second, right, of the second bounce. So what we have here is actually v down, v up. We have square root of 2gh for both of these. So we could go ahead and plug this into our coefficient of restitution, and so we're going to get square root of 2gh from the bounce all over square root of 2gh from the drop. And so what we're going to get is the square root of h of the bounce height all over h from the drop height. Or you could write it probably more simply h final, h initial. So this will kind of simplify our life a little bit since we already did all the work to derive this. So for the golf ball, we have 0.33 over 0.6. And so we're going to end up with coefficient of restitution of 0.7. So this is for the golf ball. For the ping pong ball, we got 0.88. So one thing that we could say here is that the larger the coefficient of restitution, the more elastic the collision is. So if E is 1, this is a perfectly elastic collision. So here all of the kinetic energy is conserved if our coefficient of restitution is 1. For E between 0 and 1, these are inelastic collisions, like our golf ball and our ping pong ball colliding with a table. And now E equals 0 is our final case here that we're going to consider. And so what this says is that V relative final is 0. So that means that the two objects aren't moving away from each other. So this is our perfectly inelastic collision. In this problem, we have two hockey players pushing out from a clinch, recoiling from rest. In this problem, we have two hockey players pushing off from a clinch, recoiling from rest. So initially, we have our two guys, Jean-Claude and Pierre. Let's just call this guy Jean-Claude and this guy Pierre, and their velocities are 0. We know that Jean-Claude has an inertia that's 70% greater than Pierre, so we know that the mass of Jean-Claude is 1.7 mass of Pierre. They push off and move across the ice in opposite directions. That has to be the case because if they push from each other, they have to keep the momentum of this closed system conserved. So initially, the total momentum was 0. So afterwards, we know that Jean-Claude has to be moving this way, and we know that Pierre has to be moving to the right. So they push off from each other, move in opposite directions, and then we know that the kinetic energy decreases at the same rate until they come to a stop. So the final velocities for both of these guys is going to end up being 0. So who travels farther? So we could answer this if we knew a little bit more about what does this losing kinetic energy mean. What this is actually telling us is that the acceleration, after they push off from each other, there's some friction with the ice, is going to be equal to, Jean-Claude's is going to be equal to Pierre's. So they're both decelerating at the same rate. And that causes their kinetic energy to decrease at the same rate. So what are the ratio of the distances traveled? So that tells me I'm going to have to do some kinematics. I can't just do conservation of momentum and energy. So I'm going to have to backtrack, try to find out what Vj is and what is Vp. From that, then I can move forward and start calculating some delta xj and delta xp. So who travels farther? We might guess that Pierre is probably going to travel farther because Jean-Claude has greater inertia. So Jean-Claude has more mass. So in this conservation momentum, we know that Pierre is actually going to be traveling faster than Jean-Claude. And if he's traveling faster and their accelerations are fixed, we could guess that Pierre's distance is going to be greater. So let's work this out and see if we were right in our guess. So initial momentum is going to be 0. Both their velocities are 0. Final momentum is going to be mj bj plus m Pierre b Pierre. I'm writing vectors on top of these because I haven't considered the direction yet. I'm just writing this general form out. So the mass of Jean-Claude is 1.7 times the mass of Pierre, so I'm going to go ahead and put this in. 1.7 m. And Vj is moving to the left, so that's minus Vj, the speed of Vj that I want to know, plus m and then Vp. So here I get mVp is going to be 1.7 mVj, so Vp is 1.7 Vj. And that's kind of what we predicted about the speeds of these two, in that Pierre is going to end up moving faster than Jean-Claude. So what we want is, we want distance, we know velocity, we know final velocities of both of these guys, and we know something about acceleration. What we don't care about is time, so we're going to grab this guy. V final squared is V initial squared plus 2a delta x. So we know that our final velocity of, just say Jean-Claude, he's moving this way, he eventually reaches a stop, and we want to know this distance. So that's going to tell me that this guy is 0. So when I solve for this, I get V initial squared is going to be equal to minus 2a delta x. So, but what I really want to know is this delta x, so I'm going to solve for that. And so I'm going to get V initial squared all over minus 2a. So now I'm going to start plugging in for Jean-Claude, and Jean-Claude's velocity, right, squared over minus 2a, and then now I'll do the same for Pierre. But I know that Pierre's velocity is 1.7 times Jean-Claude, so this is going to be 1.7 Vj, and that whole quantity is squared, divided by minus 2a. So 1.7 squared, I can pull that out, that's 2.9. Now I end up with Vj squared over minus 2a. What you can see is that this part in these squared brackets is the same as this up here. So what this is actually telling me is that delta x Pierre is going to be 2.9 times delta x Jean-Claude. So delta x Jean-Claude over delta x, delta x Pierre over Jean-Claude is going to be 2.9.